Hello everyone, my name is Hansen. I come from the Beijing Institute of Technology. Today I would like to introduce our paper, Learnability Enhancement for Low-Light Row Denoising, where paired real data meets noise modeling. Computational photography is widely used in many fields, such as photography, astronomy, autonomous driving, robotics, microscopy, and augmented reality. Low-light denoising is an important task in computational photography. On the one hand, residual noise is unsightly, which will affect visual perception. On the other hand, residual noise is indistinguishable, which will affect downstream tasks. In low-light denoising, learning based on methods are mainstream. The principle of learning based on methods is learning the data mapping from a noisy image to the corresponding clean image through a neural network. The key point of learning based on denoising methods is high-quality data. There are two kinds of data. One is the paired real data captured from real-world scenarios. The other one is the synthetic data synthesized according to an artificial noise model. In recent years, many low-light denoising works has also focused on the data and make amazing progress. Please look at this comparison. The first image is a noisy input image captured in low-light conditions, and the second image is a clean reference image corresponding to it. The baseline is the denoising results trained by paired real data. If we synthesize training data based on the simple noise model, the denoising network will not perform well. It is because the simple noise model is far away from the real read noise distribution. The physics-based noise model is proposed to develop the simple noise model. However, the physics-based noise model is still not accurate enough, and significant residual noise can be seen in the result. SFRN is proposed to obtain noise closer to the real read noise. Its noise model is based on real read noise samples, which helps the denoising network achieve much higher visual quality. Synthetic data methods are now generally on par or even better than paired real data. However, none of them can completely eliminate fixed pattern noise. This discovery attracts us to do an in-depth analysis. According to our analysis, we found that there is a learnability bottleneck in low-light denoising data. We expect the paired real data can be used to fit the real data distribution. However, due to the limited data volume and the real but complicated noise distribution, real-world data mapping is hard to precisely learn. We expect synthetic data with increased data volume can be used to learn precise data mapping. However, since the artificial noise distribution is always different from the real noise distribution, real-world data mapping is hard to accurately learn. Let's reveal the learnability bottleneck in the data of low-light denoising. Paired real data has a real noise distribution, but its data volume is limited, which makes the network hard to precisely learn. Synthetic data has increased data volume, but its noise distribution is artificial, which makes the network hard to accurately learn. And here's what we found interesting. The advantages and disadvantages of these two kinds of data are complementary. So why not integrate them together? Our motivation is reforming paired real data according to noise modeling. In this paper, we propose a learnability enhancement strategy for precisely and accurately learn the real-world data mapping of low-light denoising. Firstly, we propose shoe noise augmentation. It can increase the data volume of paired real data. Benefiting from the increased data volume, the mapping can promote denoised image with clear texture. Secondly, we propose dark shading correction. It can reduce the complexity of real noise distribution. Benefiting from the reduced noise complexity, the mapping can promote denoised image with exact colors. The idea of SNA and DSC originated from the integration of paired real data and synthetic data. which are assumed as two parallel directions for low-light denoising. The framework of our learnability enhancement strategy is shown in the figure. For training, we first correct the dark shading hidden in the noisy raw image by DSC. Then we augment the clean image and the noisy image to obtain new data pairs by SNA. Finally, we will use augmented noisy image and augmented clean image to train a denoiser with U-Net-like architecture. For inference, we just denoise the noisy image after correcting dark shading with the trained denoising model. Next, I will introduce the principle and the procedure of SNA and DSC respectively. First, we will introduce the principle of the SNA. Our target is to augment the paired real data without breaking the real noise model. Increasing data volume can help the network precisely learn the data mapping, which will promote the denoised image with clear texture. The proposed SNA is based on some simple physical and mathematical principles. This is the quantum nature of light and the uncertainty of collected photon numbers. The number of photoelectrons follows the Poisson distribution. Variables following Poisson distribution satisfy the additive property. Therefore, as long as we sample delta n follows the Poisson distribution of clean increments, we can achieve data augmentation without breaking the real noise distribution. The procedure of SNA is very simple. Firstly, we random sample a set of parameters for the later procedure. Secondly, we obtain the clean signal increments and the augmented clean image. Finally, we synthesize the noisy signal increments and the augmented noisy image according to the clean signal increments. The augmented noise image and the augmented clean image will constitute a new noisy clear image pair. Next, we will introduce the principle of DSC. I think it is necessary to introduce what is dark shading first. Dark shading represents the temporal stable component in the read noise, which can be regarded as the union of black level arrow and fixed pattern noise. Dark shading is similar on different cameras of the same sensor within the normal operating temperature range and widely exists on different sensors. DSC can decouple real noise into a form with higher learnability. It's extremely important to correct the dark shading before denoising in a learning-based low-light denoising method. Previous learning-based methods believe that convolutional neural network, a collection of local operations, can be used to fit data pairs to remove pattern noise caused by dark shading, but this is impossible in principle. We will show this mapping problem with the help of the example shown in the figure. For the data containing zero mean noise in the simple noise model, the mapping target is the extraction of data. However, when such a mapping is applied to the real noise, the mapping target contains the corresponding dark shading. If we directly force the mapping target to be a clean target, it will be equal to taking the right path, where the mapping problem will arise. Because the receptive field of the convolutional neural network is limited, we cannot treat dark shading at different positions differently without global position information. Nor can we use the same mapping to correct all the special patterns caused by dark shading. Conversely, if we apply DSC to the real noise first, it will equal to taking the green path, where the data mapping will no longer be disturbed by the dark shading. Because the above mapping dilemma no longer exists, the complexity of data mapping will be greatly reduced. So how can we use such a powerful dark shading correction? First, we calibrate a black level arrow by sampling dark frames at each SO. The global average of the dark frame is a black level arrow at this SO. Secondly, we calibrate dark shading in 3 steps. The first step is sampling many dark frames at partial SO. The second step is fitting the regression model to get parameters. The third step is reconstructing dark shading at each SL. Finally, we corrected calibrated dark shading before denoising for both training and inference. Our method performs state-of-the-art on public datasets. It achieves the best denoising result with the clearest texture and the most exact color. We have zoomed in on a set of images for viewing, and this is our result. Welcome to our paper for more details. The backbone of this method are all consistent, and their training setting are similar, so their performance difference only depends on the training data. Therefore, the essential learnability enhancement strategy is the only reason why our method can surpass previous work. To study the contribution of each module we proposed, we compare the performance of models trained without SNA or DSC respectively. Paired real data without any learnability enhancement appears blurry and noisy. SNA brings a small improvement in quantitative result while it promotes denoised image with clear texture. DSC brings a large improvement in quantitative result while it promotes denoised image with exact color. SNA focuses on improving the mapping precision while DSC focuses on reducing the mapping complexity. The combination of DSC and SNA constitutes our full learnability enhancement strategy, and it achieves the best quantitative result and visual quality. Last but not least, we evaluate the generalization of our method on real imaging scenarios. We collected a smartphone low-light denoising dataset by Redmi K13, which is a smartphone with an IMX686 sensor. Our dataset is more comprehensive and high quality compared with the previous image denoising dataset. For the data quality, our dataset has a less spatial misalignment, brightness misalignment, and residual noise. For data volume, our dataset has more paired real data and imaging scenarios. In addition, our data also provides a real image high-speed output and the noise calibration materials of this sensor. For the generalization evaluation, all noisy images were collected at a max analog gain and evaluated at 8 times digital gain. Our method still achieves the best denoising result with the clearest texture and the most exact colors, which demonstrates the high generalization of our method. Let me make a conclusion. In this paper, we analyzed the learnability bottleneck of low-light denoising. Based on the analysis, we decided to reform paired real data according to noise modeling. First, we proposed shoe noise augmentation. It can increase the data volume of paired real data, which will promote denoised image with clear texture. Secondly, we proposed the dark shading correction. It can reduce the complexity of real noise distribution, which will promote denoised image with exact color. Finally, we introduced our smartphone low-light denoising dataset. Extensive experiments on public datasets and real image scenarios collectively demonstrated the state-of-the-art performance of our method. Thanks for your listening. Welcome to contact me via email or WeChat. Thanks.